Hypothalamus Artificial Intelligence, HI. Digital transformation with artificial intelligence and real-time optimization. At HI, we take mathematical optimization to the next level with OPTEX-GAMS, our platform designed especially for GAMS users. As GAMS business partners, HI offers training courses in GAMS, from basic to advanced level. These courses can be adapted to the needs of each industry, providing practical tools to apply mathematical optimization in different sectors. This presentation is related to the implementation of parallel optimization models, using GAMS. Parallel supercomputing is a critical enabler of modern artificial intelligence, AI. Especially for training large models and performing fast real-time inferences, by distributing computational workloads across multiple processors, such as GPUs, to significantly speed up processing and efficiently handle massive datasets. This approach is essential for complex AI tasks, including predictive and prescriptive AI, enabling faster model creation and execution, improved performance, and the development of more advanced AI applications. Parallel processing is the simultaneous execution of multiple tasks on multiple processors or cores, where a parallel program consists of multiple processes that solve a problem at the same time, dividing a task into subtasks using the divide and conquer methodology. Each subtask is processed in a central processing unit. The motivation for parallel processing arose from the need to overcome the physical and technological limitations of single processor performance, as sequential architectures are limited by the speed of light and thermodynamic laws. The speed at which sequential CPUs can operate has reached the saturation point, so it is necessary to connect multiple processors to achieve higher computational speed, which represents an opportunity for horizontal growth rather than vertical growth. Today's applications require more computing power than a sequential computer can deliver. Parallel processing provides a cost-effective solution by increasing the number of processors and adding a communication system between them. The workload can be shared, resulting in more computing power than a single processor system offers. The development of parallel processing has been driven by ever-increasing computational requirements in scientific computing. General vision of parallel computing. Today, when we talk about parallel computing, the first element to consider is the multi-core and multi-threaded CPU, its architecture, and the software components it stores, which are presented below. Today, operating systems can run multiple programs simultaneously instead of running them sequentially. This is known as multitasking. Multitasking doesn't necessarily need multiple physical processors or multiple cores. A single processor and even a single core can share time between multiple processes. Today, processors work so fast that we have the illusion that all multiple processes run in parallel. If the computer has multiple processors or cores, different processes or tasks can be executed in a truly parallel manner. It should be noted that all processors share RAM. If you have many processors and very little memory, the parallelism effect may be lost due to inter-process interference, which can bog down the machine. Each process can create threads, known as threads, which are independent sequences of code statements. Multiple threads within the same process can communicate and share resources. Multithreading is used to improve the performance of an application by splitting sequential instructions into multiple parts. For example, a server-based application uses multiple threads to handle multiple requests simultaneously. The evolution of multithreading is in constant motion and has been the center of superservers. Depending on the CPU type, a fast cache is used to access commonly used data. Access to the CPU cache is faster than that of the main memory, RAM. Typically, the data cache is organized as a hierarchy of multiple cache levels L1, L2, and so on. The L1 cache is the fastest cache and usually comes inside the processor chip itself. It uses high-speed SRAM, static RAM, instead of the slower and cheaper DRAM, dynamic RAM, used for main memory. The L2 cache is located between L1 and RAM and is larger than L1. There may be a third-level L3 cache, depending on the type of CPU. Each core can have its own local L1 cache. There are multiple architectures for multi-core and multi-threaded computers, which becomes one more variable to be resolved. In recent years, a new supercomputer architecture has emerged, based on the power of parallelism provided by GPUs, graphics processing units manufactured by NVIDIA. This architecture is today the basis of the supercomputers that power GPT artificial intelligence. NVIDIA ChuOpt is a GPU-accelerated, open-source solver for decision optimization, excellent in mixed integer linear programming, MILP, linear programming, LP, and vehicle routing problems, VRP. Designed to address large-scale problems with millions of variables and constraints, ChuOpt enables near real-time optimization, resulting in significant cost savings. With a record in the mixed integer programming library, MIPLib, and 23 world records and routing benchmarks, ChuOpt delivers breakthrough performance in solving complex real-life optimization problems. To use GAMS with ChuOpt, you will need a Linux operating system, an NVIDIA GPU, and GAMS version 49 or newer. The research realized by Lamani et al. Consists of the implementation of the simplex algorithm in a multi-GPU architecture, using CUDA, NVIDIA Compute Unified Device Architecture for GPUs. Computational tests have been carried out on randomly generated instances for non-sparse LP problems. Tests show a maximum acceleration of 24.5 times with 2 Tesla C2050 cards. Dense linear programming problems occur in many important domains. Large-scale algorithms, such as Bender's and Danzig-Wolf, result in dense LP problems. This aspect is fundamental when the memory of the process is included in artificial brains. Synchronous parallel computing executes multiple coordinated tasks in synchronized steps, waiting for all operations to complete in one phase before starting the next. It uses mechanisms such as barriers to ensure that all threads or processes reach a common point simultaneously, which is vital to avoid problems such as race conditions and data corruption in systems with shared memory. Asynchronous parallelism is the most general form of parallelism, whereby processors operate freely on tasks and global synchronization is not required. Visual Studio Magazine defines asynchronous programming as a means of parallel programming in which a unit of work runs separately from the main application thread and notifies the calling thread of its completion, failure, or progress. If synchronous computing is not necessary, then asynchronous computing will always be faster than synchronous computing. However, synchronous computing may be necessary when an execution is required to repeat exactly, to audit the results, scientific work, and software development. Each bar indicates the acceleration ratio calculated as the sequential time divided by the parallel time. It is clear that the parallel solution is faster. Any parallel algorithm can run in 2 versions. Asynchronous, each version of the algorithm runs at the highest speed, and usually, when vacated, it restarts the cycle, and synchronous, there is a point of synchronisms, in which all algorithms must wait for the last one to finish the cycle. It is used for the control and analysis of algorithms. The image compares monolithic optimization solutions versus large-scale optimization solutions. To do this, the asynchronous version of Bender's is run for all instances, running until the same optimality gap is reached as with C-Plex after 10 hours. All algorithms run on 15 processors. The C-Plex time divided by the Bender's time indicates how many times a monolithic solution, represented by C-Plex, is slower, compared to a solution that uses large-scale optimization, arriving 519 times slower in the most complex instances. The image shows the performance comparison of the additional processors, in which it is shown that the analyzed algorithm, as the processors increase, the marginal performance gain decreases. 2 coordinators are needed for the parallel process. The CPU coordinator, the coordinator of algorithms that run in parallel. It is the possible implementation of the multi-Bender's decomposition algorithm, developed by HI aimed at artificial brains. MBD can be implemented with a unified coordinator, using asynchronous parallel optimization. In the simplest case, one processor should be assigned to the unified coordinator and multiple processors to the subproblems, ideally one per subproblem. In the case of the example, it would be 10 processors in total. 1 for the coordinator and 9 for the subproblems. A core must be free to manage the computer's memory, so, in this case, the number of CPU cores should be at least 11. HY's approach to developing large-scale superalgorithms using linear programming models as the core, in this case using CPLEX. Similarly, problems that need to be solved with different methodologies on a large scale can be shared. From a central set of equations, each problem can be adjusted according to the algorithm to be used. High-power dispatch model. Parallel implementation. GAMS programs. ModPlan. Parallel and stochastic implementation using GAMS. Deterministic optimization model. This is the standard or core model, which considers a single internal scenario. Non-anticipative stochastic optimization model. Starting from the stochastic parallel model, a non-anticipatory response is required, that is, the decision depends on what is happening in the stochastic dynamic process. In these cases, each scenario has its probability, looking for a solution that optimizes a measure of system performance by integrating the scenarios, such as expected value or other statistics. The solution must be obtained by introducing a model coordinator aimed at ensuring the constraints of non-anticipation and the optimum of the objective function. Non-anticipative stochastic optimization model. Starting from the stochastic parallel model, a non-anticipatory response is required, that is, the decision depends on what is happening in the stochastic dynamic process. In these cases, each scenario has its probability, looking for a solution that optimizes a measure of system performance by integrating the scenarios, such as expected value or other statistics. The solution must be obtained by introducing a model coordinator aimed at ensuring the constraints of non-anticipation and the optimum of the objective function. Non-anticipative stochastic optimization model plus risk management. Finally, HY considers that stochastic optimization models, in their two versions, only make sense if risk management is included. For this reason, if the modeler requires it, OPTEX can automatically incorporate financial, and/or operational, risk management equations. This is the scope of the high-power models. GAMS, utilizing multiple CPUs and cores. There are several ways to increase the performance of the solver, mainly considering hardware upgrades. A distinction is made between a single computer and a grid of computers. A distinction is also made between the case in which the model consists of a single instance, i.e., a declaration of resolution, and the case in which the model consists of multiple instances. The case where the computer has multiple cores, in a CPU, should be considered. A simplified guide to increasing computing power can be the following. GAMS, utilizing multiple CPUs and cores. Fast CPU. Enough memory, because the use of swap memory, hard disk, is, comparably, extremely slow. Multiple cores. Multiple cores. Keep in mind that a strong and adequate algorithm can use few computing resources and outperform an inadequate and weak algorithm that drains the computer's resources. Pay attention to the task manager of the operating system, Windows, Unix, or Mac, to observe how a solver consumes the computer's resources. GAMS, utilizing multiple CPUs and cores. GAMS, the grid solve facility. Installing GAMS Grid allows to take advantage of high-performance networking and computing systems with multiple CPUs and multi-threading. This feature makes it easy to manage asynchronous delivery and recovery of model solutions independently of each computer in the network. It is an open architecture that builds on the functionality of each node's operating system and allows for the rapid introduction of new environments. A typical application may use hundreds or thousands of model solution tasks that can be performed in parallel. Examples include, but are not limited to, scenario analysis, Monte Carlo simulations, Lagrangian relaxation, decomposition algorithms, and advanced solution approaches. Network functions work across all GAMS platforms and have been adapted to many different environments, such as Condor Resource Manager at the University of Wisconsin. Researchers using Condor reported a delivery of 5,000 CPU hours in 20 hours of clock time. Similarly, The multi-threaded resolution feature of GAMS enables asynchronous submission and collection of model solution tasks on a single multi-threaded machine while utilizing efficient in-memory communication between GAMS and the solver. In 2004, General Algebraic Modeling Systems Incorporated, GAMS, reported experiments in the speed gained using 200 CPUs in parallel was 60 to 1 times faster, with its corresponding benefit in accuracy, if parallel processing is used to increase the quality of the results. In addition to the effect of the hardware of computers oriented to parallel processing, nowadays practically all of them, you have to know the software to see how it will work in the selected option. In high algorithms there are different implementation options that make different use of parallelism. Each release involves variations in algorithms and therefore variations in cost. The graph presents the effect of the parallel implementation of the standard high-power/mod plan algorithm. The effects are: no parallelism, reduced use of system resources, and longer time to solution. With parallelism, increased use of system resources, and shorter time to solution. Two coordinators are needed for the parallel process. The CPU coordinator, the coordinator of algorithms that run in parallel. These coordinators may reside in the same GAMS program or may be in two different programs. In the second case, the CPU management coordinator may be coded in any computer language. High power dispatch mod plan parallel and stochastic GAMS program generation. GAMS program is presented below, with the two coordinators included in a single program. The program was generated by the artificial intelligence OPTEX optimization expert system. Only the parallel optimization part is presented and explained. The model corresponds to one of non-anticipative stochastic programming. The implementation of the parallel mod plan was carried out by coordinating everything within a single GAMS program. The methodology consisted of programming, in the same program, a part of the problem startup using a traffic light system that informs the first core that is free. Another section of the program is aimed at results retrieving, asking the traffic light system to determine which cores have completed their task, to execute the recovery process. Using a single program, the two processes are performed sequentially, which can cause waits in the launch queue, or in the recovery queue. These timeouts can be eliminated, if OPTEX generates two programs, one aimed at launch and the other at recovery. The image presents the flow diagram of the two cycles controlled by the traffic lights. The OPTEX control window part. It is related to the activation of the parallel processing option, so that OPTEX generates the parallel code. This part of the program is presented below. As stated above, in the case of parallelism, it is necessary to modify the programming to handle the process. As you can see, the sequential and parallel solutions solve the same problem, but the data flow is different, since in the parallel case the processing is distributed in multiple core. The problems are deterministic, but they are indexed to the values of the uncertainty dimensions of the model, which vary with the outermost loop that must sweep the entire combinatorics of the values of the uncertainty dimensions. Stochastic parallel models involve the coordinated solution of multiple independent problems that can be solved sequentially or in parallel. The mod plan model, developed for the ISO of Peru, works in parallel and was generated using OPTEX. This part of the program is presented below. A problem is structured in three parts: preprocessing, parameters that are calculated before performing optimization, optimization process using the solver, post-processing, subsequent calculations and storage of the results. These processes do not change, they are simply reorganized for stochastic optimization that can involve mixing and feedback of the results. Introducing the loop involves including additional processes aimed at calculating the statistics of the results and helping the convergence of the process. In addition, primal and dual variables definitions are needed to store the results. Then the strategy of parallelism will be to solve deterministic problems, as parameters of the uncertainty values. The screenshot shows the deterministic model variables declarations. The physical indexes are the same as those of the deterministic model. In addition, the indices of the uncertainty dimensions must be defined, which are 7, but 2 of them depend on other indices. Therefore, there are 5 effective indices of uncertainty. Since the deterministic problems do not contain the indices of the uncertainty dimensions, a RAM database must be created to store the results of each problem, containing the expanded indexes, physical entity indexes, in green, plus uncertainty dimension indexes, in blue. On the other hand, for each tuple of physical indices, at least the basic statistics should be stored. Value, average, maximum, minimum, standard deviation, in yellow. The screenshot presents declarations of statistical of the variables of stochastic optimization models. When solving a problem, it is necessary to store the results from the parallel solution. Creating CSV files deterministic model variables. At the beginning of the problem. At the end of the optimization process for all problems, statistics for deterministic model variables must be calculated. Deterministic model constraint declarations. Declarations of statistical of the constraints of stochastic optimization models. The control of sending problems to the core, and retrieving the results, is carried out using 2 loops, which work sequentially. Therefore, it is not possible to send and receive simultaneously. For this it would be necessary to generate other auxiliary programs. This possibility is faster. Before starting the loops, the modplan problem must be initialized, adapted to the parallel version. This involves defining aliases for indexes and sets that are required for parallel implementation. At the beginning of parallel optimization control, the first loop to be presented will be the recovery loop. Submitting process for parallel solution. The screen shows the opening of the loops of the dimensions of uncertainty and recovery process for deterministic solution. Writing CSV files deterministic model variables. Storing general results for parallel solution. And closing loops. The second loop to be presented will be the launcher loop. Loops for generate the problem for each scenario. OPTEX automatically generates the pre- and the post-processing of the stochastic parameters and stochastic sets for each scenario. This involves solving the pre-processing of the mod plan. Next step is submitting process for parallel solution. Closing loops. The final part of the process has to do with performing the final calculations, closing files, and activating other processes. When finished the solution of all problems, it is necessary to execute the following process. Calculating statistics, closing files, and statistical files. The following screenshots show the code. Calculating statistics of the variables. Closing CSV files deterministic model variables. Creating, writing, closing CSV files with statistical variables. To end the process, it is possible to run a custom process, even by the user. Non-anticipative constraints formulation. This constraint guarantees that the values of the non-anticipative variables are the same, for all internal scenarios belonging to a given set. Algorithms swarm, the actual state of artificial intelligence using artificial brains. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Thank you for your attention.